So welcome everyone to another space community of interest based in Wellington, but fortunately due to the advantages of modern technology, really we have a pretty wide footprint nationally at the moment, which is fantastic. So just to reiterate, this is for anyone who's interested in helping create a space ecosystem, industry and community in New Zealand, especially in light of a new resurgence of interest in space technologies, capabilities and exploration. And extra special this week, it's World Space Week. What is World Space Week, you might ask? It's a UN declared celebration of space held annually, every October 4th through the 10th. It's the largest space event on Earth, with about 8,000 events in 2019 that were held in 97 different countries. And these events are organized by all sorts of different organizations to include your local space community of interest, but lots of domestic and international organizations as well. In 2020, World Space Week is dedicated to satellites and their broad benefits under the theme of satellites improve life. I definitely agree. I'm sure you all do too. Quick shout out to Space Base for Emmeline and Eric Dahlstrom for their continued support. Our two Edmund Hillary Fellows who founded Space Base, a social enterprise dedicated to catalysing the space industry in New Zealand. They not only kicked off the Wellington Space Coil, but their continued support since they moved to Christchurch has been invaluable. Just a quick update on rules of engagement. There's a question and answer at the end of this. And feel free to type your questions into the chat function. But without further ado, I would like to introduce Dr. Nicholas Long. Nick Long is director of the Robinson Research Institute with a primary research in high temperature superconductivity, a founder of the program at the Institute to develop high temperature superconductivity Roybal cables, including the development of the manufacturing and characterization processes. His current interests include the application of high temperature superconductivity to space technology. Nick is the science leader for a magnetic sensor research program, which encompasses material research and development of applications in non-destructive testing. Dr. Long obtained a master's degree in physics at Victoria University and completed his PhD in physics at the University of Southern California. He then joined the Industrial Research Limited, which was a predecessor to the Robinson Research Institute in 1994. Dr. Long, thank you very much.
Thanks very much, Julia, for that introduction. And I remember Julia actually working with us as an intern over one summer a long time ago. But we'll have to reminisce about that some other time. So thanks very much for this opportunity to talk about electric propulsion for space. So the background to this talk is really that we have been fortunate enough to gain some MB funding to do a project developing electric propulsion for space, and in particular using superconductors, the high temperature superconductors that we're specialists in here. So the talk this evening, I'll talk a fair bit just to introduce electric propulsion for space. I'm not a space expert. I'm not an electric propulsion expert. So actually it was good for me to sort of put this together. So it's something I've been learning about over the last couple of years, really, what electric propulsion is and how superconductors might benefit. But yeah, I'll talk first about electric propulsion, and then we'll get into what we have to do to make superconductors applicable and have them make a difference. So just First of all, just a hat tip to the team that's going to be working on this. There's quite a number of us at the Robinson Institute. A lot of these people are superconductor experts who are becoming space experts. We do have a few space experts. Jacob Glowacki, some of you may know. Chris Atchison is a PhD student who has a background in space work. We're also working with John and Nick at Auckland, who many of you will know. Chris Hahn at the University of Canterbury, who's an expert in ADAC systems, among other things. And we're also working with Avinash and Malcolm, who come out of Rocket Lab. They now have a consultancy and a spin-off company, Argo Navis. So we're working with them on this as well. And in the power conditioning, David Wright, who may be known to you as well. So we really did put together the best team we could find in New Zealand. So we knew we didn't have all the credibility, particularly to do a space project. So that's why we got all those people involved. So we really knew what we were talking about. So just a quick look at the contents. I'll just look at the basics of propulsion, just to set the foundation for what we're talking about, and the limits of chemical propulsion and why you then might go to electric propulsion, and just some limits on that. Just a quick bit of early history, and then look at the different types of electric propulsion, and then we'll get into superconductors and what superconductors can do for us. So to start with something that most of you probably know better than I do, but if you're not an equations person, don't be put off either, because I'm not going to dwell on this, and the point I'm trying to get across is fairly straightforward. So this is just Newton's laws really applied to a rocket. Mass times the acceleration, which I've written as v dot. So that's dv by dt, if you're not familiar with that notation. And that equals m dot times the exhaust velocity of your propellant. So this is the rate at which you're losing mass, and this is the speed at which that mass has been thrown away. And of course there's gravity there as well, but we're going to ignore gravity after this slide. So with electric propulsion, we're actually talking about fairly small thrusts, fairly small forces. They're not forces large enough to actually get you off the ground. Here's the Electron rocket getting off the ground. So we're going to ignore gravity, and electric propulsion is of use when you're already in orbit. You're already escaped the, well, you've done the work that you need to do against the force of gravity. So just a couple of definitions. The thrust is this term here, the m dot times your exhaust velocity, and the total impulse is integrating that thrust from start to finish. Now, if you want a large thrust and a large total impulse, then that implies that a large exhaust velocity is needed. I mean, you could make this term large, the thrust large, by having a large rate of mass loss, but that would imply you'd need to start with a whole lot of mass to begin with that you're willing to dispense with, and that's expensive in all kinds of ways and creates system problems. So having a large U exhaust velocity is obviously better. If you ignore gravity, you can integrate that equation of motion to find the total delta V that you would have for your rocket, and that equals this exhaust velocity times the logarithm of your starting mass over your final mass. And we're not going to do much with this equation except just to note this logarithm here. So if you know how logarithms behave, to make that a large number, you would need the initial mass to be orders of magnitude larger than the final mass. So again, you'd have to, be willing to dispense with lots and lots of mass in order to have that as a large number. So clearly, if you want a large delta V, if you want to change the velocity of your satellite or spacecraft, ideally you really want this U again to be very large. And in fact, you want it to be as large as delta V. So missions themselves can be characterized by a delta V. You have to make some simplifying assumptions about, the orbits that you'd leave from or return to and so on, and how you do that. But just to orders of magnitude, which we're interested in here, here are some delta Vs for different missions. So to escape from the Earth's surface, you need a large delta V, about 1 × 10⁴ meters per second. If you're already in a 500-kilometer orbit, you don't need so much. That's about a factor of 3 less. And here are some delta Vs for planetary missions. In the first case, I wrote the one for going to Mars' surface and return. That's 3.4 × 10⁴ meters per second. A little bit less to go to a Venus orbit and return. So that's something Peter Beck is obviously very interested in doing that. Well, maybe not returning. Of course, returning makes a big difference. If you're just going there, you can you need something closer to this value. And going to Mercury and returning, or to some of the gas giants and returning. So these numbers are large, 10⁴, getting up to 10⁵. So chemical rockets have a limit on the exhaust velocity. So we want this large exhaust velocity, but with a chemical propellant, it's limited by the chemical energy that is available within your propellant when it goes through combustion, and also the material factors. So the speed at which ions and so on move can be related to the temperature. So very, very high speed implies very, very high temperatures. At some temperature, you're going to start to melt the inside of your rocket or your combustion chamber. So these are some values for different liquid propellants. So you can see these UEs are a few thousand for the usual propellants. As you get up to more exotic propellants, they can go a bit higher, 4,000 to 6,000. So you can see these numbers are well below that delta V that we required for interplanetary travel, for example. So they're too low for those interplanetary missions. You really can't go to Mars and back using chemical rockets. You're going to need something else. One solution is literally to go thermonuclear. That is, you start using nuclear energy to heat your gases, and there are spacecraft that do that. But that's not the topic of today's talk. We are going to talk about another option, which is electric propulsion. So a definition of electric propulsion is the acceleration of gases, and usually we're talking about ions or plasmas in some form, but the acceleration of gases for propulsion by electrical heating and or by electric and magnetic body forces. So that's our definition. So to get up to these very high exhaust velocities of greater than 10⁴ meters per second, we really need electric propulsion. So there's 3 different types that I'll just mention briefly. One is electrothermal propulsion. So this means we're going to heat the gas electrically and then allow that gas to expand in some nozzle structure. So we're not applying electric and magnetic fields directly on the ions. We're sort of indirectly heating the ions. Another method is electrostatic propulsion. And in this one, we accelerate the ions with electric fields. So if we had a set of positive ions, we put them in an electric field, a constant uniform electric field, they will accelerate. So that's fairly straightforward, although it comes with some complications, as we'll see. The other category is electromagnetic propulsion. And fairly simply, this just means we're going to accelerate the ions with both electric and magnetic fields. So we can take advantage of the Lorentz force available from magnetic fields, as well as the the Q times electric field force. Just a point of comparison on these speeds, 10 to the 4 meters per second. So that's about 10 times a rifle bullet. In fact, it depends. I mean, rifle bullets vary a lot. Most would be well below a kilometer a second, maybe half of that or so on. But I just thought it might be useful for people. So this is pretty fast speed. But I just thought it would be useful to talk about what the limits are to that speed. So you might think, okay, speed is good. So let's just go crazy and, why stop at 10 times the speed of a bullet? Why don't we go up to 99% of the speed of light, something like that? Build a little accelerator. We can throw those ions out at any speed we like. Well, there is a problem with that, which I'll just spend this slide explaining. First, let's define the specific impulse. So this is another characteristic number of thrusters, which is often used in analysis. So it's the thrust divided by the rate of propellant use divided by gravity at sea level. So it's given by this expression. Oops, that should be, oh, sorry, these should be m dots, sorry, but they cancel anyway. So, so the specific impulse is proportional to the exhaust velocity divided by gravity at sea level. So essentially, you can just, it's just this speed we've been talking about divided by 10. Now, here we go. So we also have to think here about energy conservation. So if we're going to throw these ions out, where does the power come from? So first of all, there's going to be a weight loss through the propellant ions. So we can think of delta M, the amount of mass we're losing in some time, delta T. So delta M is our rate of mass loss times delta T. And if we just use our definitions of thrust, we can get the thrust over our exhaust velocity, that's the same as m dot. And we can use this definition we had over here to introduce the specific impulse. So this is our delta M in terms of thrust and specific impulse. Then we also need to supply the power. So this is the key point. We need some mass associated with delivering that power. And we can just assume that it scales as alpha. So the more power we have, the more mass we're going to have. And we can also assume that there's some efficiency factor between power that we have available via a solar cell or stored in a battery and the power that's actually going into the ions. So that's just another constant. So it's the rate of change of this half m u squared, and we can work that through again. So U is constant, so we have an M dot again, and we can again replace that with our characteristics of thrust and specific impulse. And what you'll see if you plot these two functions, well, if you plot the sum of, if you plot these two functions and the sum of these functions, so if you plot mass versus the specific impulse, what you see is the mass associated with power is keeping on going up. The delta M goes down. So the higher the specific impulse, the more efficiently we're using the fuel, if you like. So we're getting more and more efficient. So this is our throwing things out faster and faster. But the energy is going up very fast. So that means the mass that we need to supply that power is going up very fast. So at some point, this becomes ridiculous. You can't just keep getting bigger and bigger solar cells, arrays and arrays of solar cells to supply all of the energy you would need to accelerate these ions to, to higher and higher speeds. So there is an optimum in terms of the efficiency of payload in terms of this function. So this number is a sort of an optimum for the payload fraction of mass for this system. So this is a simplified analysis, and there are other complications which can come into it, but nonetheless it is generally true and just worth keeping in mind. So it's not a case of just go faster and faster with your exhaust velocity. There are some limits that come into that. So just a little bit of early history about electric propulsion. Apparently it was recognized even in the very early days by Goddard. I think this is just in conversation with people. He recognized that the ability to propel ions from a spacecraft in some way other than chemical means would be important in the future. Nothing really happened substantially until I think the 1960s, when R&D programs really came along. 1970s, the Soviets started experimenting with Hall thrusters on spacecraft. 1980s, there were commercial application of Resistojets. So these are the thermal heating systems for station keeping and attitude control. 1990s, there were electrothermal arc jets used in geosynchronous satellites. 1994, electrostatic ion thrusters for north-south station keeping of commercial satellites, and 1998, electrostatic ion thrusters on a planetary NASA mission. I think this was actually a mission to an asteroid. So by the end of the 20th century, electric propulsion was generally fairly well established. And that development has continued. So, for example, the arrays of satellites that are going up today, such as the Starlink satellites, all have electric propulsion systems on them. So just to talk briefly about these three types, there's the thermal heating, thermal expansion types, the Resistojet and arc jet. I'll just mention briefly about them. The electrostatic acceleration, these are some of the major types there: the gridded ion thruster, the electrospray, and the Hall effect thruster. The Hall effect does have a magnetic field, but that magnetic field doesn't directly accelerate the ions. So you could argue about which category that goes into here. And then you have types of electromagnetic acceleration, the Magneto-plasma dynamic, which is the type that we're going to be concentrating on, but there are also others: pulsed inductive thruster and pulsed plasma thruster. These all have similarities to each other, and in fact depending on how you operate these systems, they can be considered as sort of hybrids of some of these things. All of these systems sort of have different regimes where they're capable of operating. So some will be better in terms of the thrust per available power. Others will give much higher specific impulse. Just a note on power categories. So often when you read about electric propulsion, you'll hear about low power and high power systems. So just a note on that, low power systems generally mean less than a kilowatt. So there are already a number of systems out there in this category. Generally, the research that's going on is to increase the efficiency of those and the reliability of those. Obviously, reliability will always come into anything that needs to be deployed in space. Moderate power is sort of 1 to 20 kilowatts. High power is greater than 20 kilowatts. And this is where there really hasn't been much work on electric propulsion systems. So the research goals there are really around increasing the specific impulse and the longevity of those systems. So this is where really new development is going on to develop systems capable of doing those planetary missions. So just very quickly, I'll talk about just one from each of these categories. The Resistojets essentially have heating coils with which the gas comes into contact, and that heats that gas directly. It's limited to about 3,000 Kelvin. If you know anything about high temperature research, 3,000 is definitely getting up there. There are not many materials which can survive long at those kind of temperatures, particularly if you're directly impacting charged gases on them. The exhaust velocities are modest for these systems, and the thrust is modest, but still very respectable for something which is of that power rating. Usually powered with hydrazine and used commercially. And some of the first commercial uses were these satellite systems, communication satellite systems. The gridded ion thruster. So now we're in the second category of electrostatic acceleration of the ions. So in some ways this is fairly straightforward. You need some sort of ion source, which can itself be quite complicated. So we've just ignored any complications here. We've just said suddenly we appear a whole lot of positive ions. We've got a large voltage between the ion source and an electrode. And this electrode has to be perforated in some way. So it has to accelerate these ions and then allow the ions to pass through. The other thing it has to do, or the system has to do, is after the ions have passed through, it has to neutralize the ions. So there has to be this neutralizer system, some source of electrons here, so that the plasma is neutralized. If you didn't do that, of course, what you'd be doing is emitting a whole lot of positive charge from your spacecraft, which means you leave behind a whole lot of negative charge. So at some point, that's not going to work. At some point, all that positive charge is going to want to come back again. So you have to neutralize the charge. These velocities can be extremely high, and the power range can be from the low end up to the moderate range. Oops, I'll just go back. The one problem with this system is that it has a very low thrust density. So if you consider this diagram here, you've got all these positive charges which you're bunching together. and there's only so much density that these charges will tolerate before they want to spread out. So they're not going to nicely stay in a straight line here if you've got some very high density of positive charges. So that limits the operation of these systems to low density gases, or low density, ions here, and that means you've got a low density of thrust. So that is a fundamental limitation with these systems. So one way to get around that limitation is to go to these electromagnetic thrusters. And the type I'll talk about is the Magneto-plasma dynamic thrusters. And first of all, we can talk about ones which are referred to as self-field MPDs. So that is, there's no external magnet or coils providing the magnetic field. So an electric current flows in some ionized media. But on the whole, that media is neutral. So there's as many positive as negative ions. So it doesn't have this problem that you have to later on neutralize the ion flow. So for that reason, it can have a much higher thrust density than the electrostatic thrusters. So the basic idea with these electromagnetic thrusters is that you're going to have some electric field in one direction, a magnetic field in another direction. There'll be a current flowing along the direction of the field, but then there'll be a Lorentz force, which is J cross B, acting on the ions. And as in this case, the electrons flow down this direction, they will transfer their momentum to the ions in the plasma. So the whole plasma will accelerate in this one direction, giving you a force. So what that looks like in a little closer to reality is here's a schematic of a self-field MPD. So you've got an anode on the outside, cathode on the inside. So you have those currents flowing between the anode and cathode. The very strong currents flowing through the cathode and then through the plasma give you a self-magnetic field. And then the interaction between the ions and that self-magnetic field produces a force on the ions. So in a lot of ways, it's a very simple system. It's a system that can be scaled to large powers. The only drawback is that the very high currents can cause ablation of the cathode, and so you can get lifetime issues with these systems. The next alteration you can make to this is to go to an applied field MPD. So now we've got coils surrounding our anode and cathode, which supply the external field. So that means we can go to much higher fields than for the self-field system. And so we can get a larger, J cross B term without having to have such large currents flowing and causing these lifetime issues. Or at least one would hope that's one byproduct of being able to do this. The electromagnetics is fairly complicated in these things, but again, so you have a motion of the plasma out of the nozzle, and it picks up this axial force from the combined effect of the electric and magnetic fields. Okay. So the motivation for our project is really this ability to go to high field with superconductors, which I'm going to talk about shortly. And there is a variety of modeling work in the literature which says going to higher magnetic fields could be a really good thing. So this is a plot of the efficiency of an MPD thruster versus the specific impulse. And you can see you're getting higher efficiencies as you go to higher magnetic fields. So this is a 1 Tesla field here. So that's got to be a good thing if we can get higher efficiencies. There's also evidence, and you would expect that you can get higher thrusts as you go to higher magnetic fields. So again, this was some modeling work that's been undertaken, just showing generally that you'll get higher thrusts with higher magnetic fields. So that's our motivation. Can we get higher magnetic fields, apply them in these MPD thrusters? So the way to get higher fields is to use superconductors. And I'll just briefly describe the material that makes up the superconductors we're going to use here. So a superconductor, for those who don't know, is a material which can carry DC electrical current with no resistance. So that's a good thing straight away. You're not going to have any I squared R, any ohmic losses in your magnet. What is also very important about superconductors is they have extremely high current densities. So in this wire here, which I'm sorry you can't read the writing, this is a 4 millimeter wide wire. It's only about 0.2 millimeters thick. And it can carry a couple of hundred amps at 77 Kelvin. So that's about 1,000 times more than copper could carry under the same conditions. So the wire internally looks like this. So it's a very complicated stack of materials. The reason for that is the crystalline quality of the material has to be very high. So it's only this internal material, the rare earth, barium, copper, oxygen material is what's actually doing the conducting. So in these wires, it may only be something like 1.6 microns. But the density, the current density in that material is about 1 million amps per centimeter squared. So much, much higher, orders of magnitude higher than copper. And that means you can have these other materials, support materials and copper stabilizer materials without significantly losing the current density. So just briefly, some pictures here of showing this wire being wound into a coil. So you can buy this wire in lengths of hundreds of meters. You can wind it into a coil, which will end up looking something like this. For our application here, we're probably talking about much smaller coils than this. But this is a relatively large coil here. So just again, illustrating this idea about current density, these are cables which would carry about 1,000 amps, possibly, copper cables. So that's about 2,000 amps. This is some superconductor, a small amount of superconductor cable, which can also carry 2,000 amps. So that's the advantage you get with superconductors. So you're carrying the same amount of current in a much smaller cross section. It's much lighter, and you don't have any losses. So that means you're not having to supply energy for those losses either. So that's all the good news. One thing you'll know, of course, is that they do have to operate at cryogenic temperatures. So that means you do need to attach a refrigerator to them. So that's the disadvantage. But the good news is there are space qualified cryocoolers available. And this is one of them here from a company called SunPower. So this cryocooler will operate at between 77 Kelvin and down to about 40 Kelvin. This length here is 242.8 millimeters. So This isn't the smallest cryocooler available on the market, but it would be typical for a small cryocooler. It can be powered by a 24-volt DC power supply, weighs 2 kilograms. So just as an example of the type of cryocooler available. How these work, this is the cold tip, which you would attach usually to a copper plate, which is then physically in contact with your superconducting coil. So you've got conduction cooling with these systems, would be the normal way to do that. This the pressure vessel. There'd be the hot end would be here, and this is the cold end here. So that's about. So these run on a Stirling cycle. For those who know something about their cycles. Yeah, there's nothing really nothing magical about them. They're just a thermodynamic cycle, a mechanical cryocooler. So they do have moving parts, but they're very well optimized. Mean time to failure 200,000 hours for these systems. So they've been very well developed mechanically and are incredibly reliable. I'll just talk about one other thing. So the other thing, of course, we need is a power supply. So we've got our coil, which we might be running a few hundred amps through. So we need a power supply to supply that current. But superconductors allow you to play a very nice trick here. And that is that we can get that current inductively rather than through a usual electronics-based power supply. So normally if you inject current into a superconducting coil in some cryostat, you're also injecting heat. And that's because to go from the outside to the inside, you need a copper lead, and there are I²R losses in those copper leads, and there's also heat physically conducted through those leads. But if you could induce the currents in here, rather than having these current leads, you wouldn't have those losses at all. And that's something that can be done through what we call an HTS, that's high temperature superconductor dynamo. So this is a simple illustration of what that looks like. In this case, we've got rotating magnets, but you could do this electromagnetically and create a traveling magnetic wave. So you don't actually have to have rotating elements. And if you rotate these magnets past a superconductor strip, you actually induce a slight current in the superconductor. And the coil can then act as an accumulator, essentially, and you can build up a current in this coil simply by rotating the magnets. That means you can have this magnetic field actually separated from the superconductor by your cryostat wall. So you can actually take the power supply outside the cryostat wall and not have any physical connection across them. So this is just an illustration of our dynamo working. So it just rotates past. This is our superconducting tape, our coil. You can do it with a permanent magnet, or you could have a set of electromagnetic coils here, which just provide a small magnetic pulse. These are a set of machines that we've built, which will supply a slowly increasing amount of current as we've built these up. So our first machine supplied about 50 amps, and then we went to hundreds of amps. These later machines can supply kiloamps or so at liquid nitrogen temperature. So these systems, we haven't made any attempt to miniaturize these, but it certainly would be possible to make these smaller and lighter and then use them to excite the magnets that we're using for space. And just a little bit about the performance. Yeah, so that they have a current voltage support curve, which looks like this, a load line. So that, in this case, the circuit current was able to go up to 1500 amps approximately, and these are very low output voltages. Of course, you only need a very low output voltage to drive a superconductor because there's, in a sense, no resistance. So, so this voltage is essentially driving the joints to the superconductor coil. Okay, I don't think I'll say much more about that. The only difference, this was a comparison between a system where we had a power supply and current leads, and this was where we had the dynamo. And you can see we've got about 1/3 of the total power required for the cooling system by having that dynamo system. So thermal management is going to be absolutely crucial to operating superconductors in space. So even though the coil itself won't generate much heat, it does have to be structurally held in place, of course. So there will be some conduction losses, and there'll also be radiative heat conduction to the coil. So because, of course, power is of such a premium, all of that needs to be modeled very carefully and managed very carefully if this is to be viable. So I'll just show in the next few slides a bit of work we've done on thermal management. We looked at a 3U CubeSat as an example, containing an HTS coil. And the team put that on a polar orbit here. And then we've calculated the radiative heat transitions. So from the solar, the albedo, and the infrared. So these are the vectors of that radiation impinging on the CubeSat and how it changes during the orbit. And then this is a illustration of how that changes over the orbit, the actual incident radiation during the orbit, and the CubeSat temperature. So in this case, we haven't shielded the CubeSat at all. So this was first of all just illustrating whether we're getting the right shading behavior and so on. So we tried it without any shading of the CubeSat. So you can see the CubeSat temperature varies from about +40 degrees C to about -40 degrees C. And that's sort of roughly what you'd expect for most CubeSats, I believe, in orbit, if you weren't doing anything to, to moderate the temperature. This is just an illustration of what our superconducting coil would look like, and just a very simplified version. So here's our Cryocooler, a physical connection to copper plates, which conduction called the HTS coil. Okay, in this next slide, we've now covered our CubeSat in solar panels, and we're still showing the incident radiation and the CubeSat temperature. So obviously the temperature is now much more homogeneous across the CubeSat. And in these diagrams in the center here, we are showing the temperature of the satellite and the Cryocooler, and also the HTS coil. So the HTS coil is steadily going down in temperature, So it's taking a few orbits in order to get there. So it's not super fast in terms of cooling down. You have to give it a bit of time. We've used a mechanical efficiency of 1. So that is, we're just assuming that it operates at the Carnot efficiency, which won't be exactly true, but it's good enough for a first calculation. So this is estimates of the solar power that would be available and the cooling power that would be available as we operate the Cryocooler when we've got available solar power. The efficiency of the Cryocooler also changes during this cycle. So that's because the hot end temperature is changing, therefore the Carnot efficiency changes. So we do have a variable efficiency of our Cryocooler to take into account as well. But generally this looks quite positive. We're able to get down to a temperature where we can operate our superconducting coil. So it is quite a complicated calculation. There are a number of variables that we can tweak in order to alter how fast we cool down and how far we cool down. So obviously it depends on the heat load, and that can depend on the amount of structural support we need for the coil. It also depends on how well insulated from radiation the coil is. So we haven't particularly done much work on that yet. Also, if you have higher input power into your Cryocooler, you can it can work it harder basically and get down to a lower temperature. Also, if we can lower that hot end temperature, the Cryocooler will operate more efficiently and get down to a lower temperature. So these are some cooling curves giving the cooling power available from the Cryocooler versus the cold head temperature for different groups of input power. So 30 watts, 60 watt and 90 watts are the input power to the Cryocooler. These temperatures are the hot end temperatures. So as you'd expect, higher hot end temperature, less cooling power available, more input power, more cooling power available. I just thought I'd mention here a project that came to our attention, something called the Cryocube satellite, which I believe is flying at the moment. So it was developed in a NASA project. But what they did here is they don't have any cryocoolers on board at all. They're just relying on passive cooling and shading of the CubeSat from solar and albedo radiation in order to get down to low temperatures. So just with that passive cooling, they were able to get down to about 120 Kelvin is the lowest number I saw with a quick look at their publications. So that to me is very positive actually. So the lowest temperature we were getting to was minus 40, but 40 centigrade. But that was without taking any particular interest in shading the CubeSat or going to any sort of extraordinary measures to lower that base temperature. So that says that you could actually lower the base temperature quite substantially if you're clever about how you shield your CubeSat from radiation. That means if you have a much lower base temperature, even if you still need a Cryocooler, it's working at such a low base temperature that it's not going to need so much power in order to expel that heat at the lower base temperature. So that suggests there's a lot of room here for clever engineering. Okay, what are we going to do? I am getting to the end here. We are going to design and build an MPD thruster with a superconductor applied field module of about 1 Tesla is our goal. Our goal is also to use an inductively powered coil. So we think that can give us, significant weight and energy savings for the whole system. It lowers the amount of cooling power you need from your cryocooler and so on. We'll then characterize that thruster on the ground, of course, at first. So we need to be able to measure its thrust and specific impulse on the ground. That won't be trivial. This will be a small thruster, so the amount of thrust is going to be, in the millinewton range, probably. So that's not a trivial measurement, and we will be working with international partners to help us with that. We're then going to integrate it in probably a 6U satellite will be needed to house both, our thruster and power supplies and so on that we need, solar panels and so on. And then we will launch that with Rocket Lab by 2025 is the goal. And I believe that will be the first time, well, certainly it'll be the first superconducting MPD thruster tested in space, if we can meet that schedule. And then, of course, we want to measure the thruster performance actually in flight on that mission. So that is our goal that we've set ourselves. So I hope that I've convinced you that electromagnetic propulsion has enormous promise for the future, that superconductors may be the way to get to much higher thrusts, higher specific impulses, and be able to do some of these planetary missions, as well as also, if they have the high efficiency, be able to use them for, Earth orbit satellites as well. So thank you very much. Wonderful to be able to talk to you.
Well, I'm convinced. I'm sure everyone else is too. Fantastic discussion. Could I ask everyone to start putting the questions into the chat function below? In the meantime, while people are doing that, can I ask a couple of my questions? I'm just going to be cheeky.
Sure, please go ahead.
So you mentioned the electromagnetic Magneto-plasma dynamic thrusters, and you mentioned how you could find some life expectancy constraints. And I was looking at the life expectancy of the cryocoolers, which was pretty generous. What's the thruster life expectancy, or is that something still to be measured?
I don't have a number to hand for you. I think if you looked into the literature on the MPD thrusters and the, particularly the self-field MPD thrusters, there are, people have found constraints there, where they have burnt out after a certain time. So that has been a concern with that technology, or at least it's a constraint on that technology. You have to understand what currents can you run them at without unnecessarily ablating away your electrodes.
Super important. So another question, how does the mass of the thruster compare with others with similar specific impulse?
Yeah, another good question. And I think that is something which we hope to answer as part of our program, and particularly how it scales with power. So I think most people would agree that at very high powers, these superconducting systems make sense. So in general, superconductors make sense at larger scales because you always have this penalty of having to have a cryocooler there and a cryostat. So although you're gaining on the current density, you're losing on cryocooler and cryostat. So for example, for terrestrial transformers, superconductors make sense at sort of 1 MVA, you know, upwards. Or yeah, and other motors and so on people have made with superconductors, they make sense at the sort of MVA scale. So it's unlikely this will make sense at a very small scale. The question is, how small can you go and it still makes sense? You know, can you, by not having a power supply, by having very efficient cooling systems, so you've got a good low base temperature, can you make this all efficient enough that it'll still make sense at a smaller scale?
All right, we got a ton of questions coming on in. Many thanks, everyone. I knew this would be, I knew this was going to get a lot of interest. Could you cite any, are there any, you did mention NASA's Cryocube satellite that use sort of non-technical answers. Are there any other similar or related research projects that are out there that are similar to what you're working on?
There are. So I can tell you that there are a number of you know, international aerospace companies who are working on you know, various forms of electromagnetic propulsion. A lot of them are definitely interested in systems which are closer to sort of the ramjet type systems. So, you know, low Earth orbit systems. There have, yeah, so also, well, there's a number of people working on electric propulsion, of course, of various sorts. Was the question about specifically superconducting systems or just?
You know, it left it up to you to define it. However, you did touch on someone else's question, which had to do with regarding using an attached payload on the International Space Station, you know, LEO orbit and everything. So that's fantastic. Let's have another look. We've got questions racing on in. Thank you, everyone. Have you given any thought to looking at commercialization opportunities and how it might advance your development schedule?
We are certainly very interested in that. And I think it's been good to have people like Avinash and Malcolm involved, because, you know, they come out of Rocket Lab and they're much more in the, you know, let's build it, let's fly it in the next couple of years and see what happens. They're much more in that mode than the academics on the team. I think the opportunity is really here to go faster, and because, I mean, it's interesting, if you look at a lot of the electromagnetic propulsion work, it evolved very slowly, and not much of it, particularly these higher power systems, not many have been flown at all. You know, there's a lot of ground-based research, is my impression. And I guess that's because flight has been very expensive. And, you know, so the big space agencies have concentrated on sort of large ground-based programs. I think in New Zealand, you know, the philosophy is a bit more, you know, let's fly something quickly and see if we can make it work and work from there. So I think we're looking forward to trying to do that, trying to get there as fast as we can. There is a lot of science you can do, though. The modeling of these electromagnetic systems is not trivial. So there are a lot of variables in the geometry of them. You know, the field ranges you're operating them, the current ranges. So there you can get lost forever doing modeling of these systems. So we'll have to sort of compromise between doing enough modeling to know that we're on the right track, but enough experiments and flight to actually show we can do it.
The constant struggle. I have a slightly different question. if you can't answer it for a variety of reasons, that's no problem. Congratulations on the funding of the Supreme technology. Are you considering Pi Solutions, the University of Stuttgart, or Neutron Star Systems amongst your international partners?
Okay, well, shout out to Marcus and Manuel. Yeah, so we did make an offer to work with them as part of this. Exactly what we offered didn't quite work out, but we'll be happy to talk to them again and work with them in some way. So yeah, there is a lot of interest in doing this in Europe and in the US as well, and particularly the interest from Europe was for the high power systems. If you want to go to Mars, you really need to have one of these systems sorted out for yourself. So I think there is, there's a lot of interest in getting this right and making it happen.
Fantastic. Bit of a question on alternative technologies. Given you have enough power, did you ever consider, say, using a specific example here, pelty elements for cooling?
Yes, well, certainly we've considered it. So in the lab, we do that. So sometimes you don't have quite enough cooling power because your hot end is slightly too hot. And so you can put on a peltier cooler and gain a bit of, get a bit of benefit that way. Passive cooling would be better. So our first option would be to go to passive cooling and see if we can get that hot end temperature down that way.
That NASA project sounded really, really interesting.
Yeah.
So the next question, are there still opportunities to work on this interesting and fascinating project?
Yes, definitely. So yeah, we're always interested in working with people, and there are many aspects to this. So there's always the chance to go deeper in some areas. And of course, there's a lot of other potential applications of superconductors in space as well. So that would be another whole talk. But I think once you've sorted out how you can use superconductors in space, you can then think about, magnetic shielding, magnetic braking. There's a lot of other interesting things you can try as well.
Fantastic. I'm going to go to a slightly more technical question. In one of your recent publications from your research group, you predicted the mass of such a thruster at around 58 kg. How do you plan to integrate this within a 6U CubeSat, considering the supporting subsystems needed?
Yeah, I think we can do it for a lot less than 58 kg. I'd have to look again at that. That publication.
No problem. Are there any relatively near-term advances in superconductors that could help this project?
To be honest, I'd say probably not. Although we keep working on new superconductors, and there's a lot of work on new superconductors around the world. What you need for space is something that's relatively mature and available commercially. So because you don't want too many parts of your system to be at low TRL levels, for example. So to put it that way. So having wire that we know works and is robust, we can always buy more of it, is important. If it was sort of a highly experimental superconductor that was, just discovered last year, that would add a whole lot more complications. So I think you've got to take what's available and robust, use that. yes, down the track, if superconductors get better, then this technology gets better. So that'll help.
Mature technology. Excellent. I believe that might be the conclusion of the questions, which is those were some. There is a last one to do with wireless power transfer and some advances out of Auckland University's engineering school that happened a few years back, and if there was any particular cooperation or synergy that might be seen there.
Probably not for this project. I do work with that team on another project. So generally the transfer they're doing is at sort of kilohertz level, say for electric vehicles, it's 85 kilohertz level transfer. So for a superconductor, that gets lossy for technical reasons we won't get into. What we're doing is a sort of inductive power transfer with that HTS dynamo, but it's a very low frequency inductive power transfer.
Yeah, fantastic. Okay, and so we're going to be all looking forward to you launching in 2025 on Rocket Lab, right? 5 years to go.
That's right. The countdown begins.
Yes, exactly. Bit of a sprint at this point, I imagine.
Yeah.
So if there are no further questions, I would like to say thank you to Dr. Nick Long. Thank you to our audience who had a lot to say.